Hello everyone, welcome to my talk. My name is Keren Zhou. I'm a graduate student at Rice University. Today we're going to talk about a GPU performance advisor based on instruction sampling that guides you transform your code to improve its performance. So performance optimization of GPU kernels is difficult. Typically, we can divide the whole process into several steps. In the first step, given source code, we can apply different compiler options to compile it into executables. Then using profiling tools, we profile its performance and dump some performance reports. By analyzing the performance reports, we gain feedbacks and using the feedbacks to change source code and profile the program to see if there's any performance speed up. In this work, we're going to focus on step 3, analyzing performance reports to gain feedbacks. We can use existing tools such as on-site compute or on-site system to gain some shallow insights because they don't tell us what optimizations are the most effective for individual lines on GPU kernels. The lack of efficient GPU tools is a big problem, and this problem is exacerbated by increasing complexity of GPU programming models and architectures. We can measure the complexity of programming models by using the number of pages in CUDA programming guides. In a very early version of CUDA, like CUDA 2.2, there were only 140 pages. However, with the most recent CUDA 11.2, it has been growing to about 400 pages. So we can see the complexity has been grown by 2x. To demonstrate the problem, we profiled the hotspot code in the Rodinia GPU benchmark. By using on-site compute, it tells us there's high short scoreboard stalls on line 4, and it suggests that warps were waiting for a short scoreboard dependency operation. However, it doesn't answer the following 2 questions. First, we don't know what instructions caused the stall. Besides, we don't know what optimizations are effective for eliminating the stall. In contrast, GPA's performance report provides comprehensive information regarding how to transform the program to improve performance. GPA analyzes the program's source code, assembly instructions, and stalls to derive that on line 4, floating point type conversion instructions cause the stall. Regarding what optimizations are effective for eliminating the stall, GPA suggests that we can apply strength reduction optimization to improve the performance by 9%. Besides, it also provides some hints regarding how to transform the program. It provides information such as avoiding type conversion instructions that demote a 64-bit float to a 32-bit float. So in this case, we can demote this 2.0 from 64-bit float to 32-bit float. GPA is a GPU performance analysis tool that identifies hot GPU kernels, reasons about the cause of slowness, suggests the most effective optimization strategies, and estimates speedups for each optimization. Note that GPA doesn't modify source code, and it doesn't guarantee 100% accuracy of speedup estimate. So essentially, GPA works like an academic advisor who suggests approaches to achieve high scores, but doesn't complete homework and exams on your behalf. Here's GPA's framework. GPA has a GPU profiler that records GPU binaries loaded at runtime, and profiles consists of instruction samples. GPA has a static analyzer that analyzes the GPU binaries to extract control flows annotated with instructions, program structures that tells us the start and end of each GPU functions and loops, and GPU architecture features such as the latency of each instruction and the throughput of each unit. Then GPA has a dynamic analyzer that takes in the profile and static analysis result to dump a raw advice report. In this raw advice report, we can get information about what optimizations are effective for a given program. We also construct a GUI tool to visualize the stores on individual lines, loops, and functions in GPU programs. In this talk, we're going to focus on this part. To begin with, we use instruction sampling on GPUs, NVIDIA GPUs to collect instruction samples. Inside each GPUs, we have several stream multiprocessors shared a common L2 cache. Instruction samplings work on individual SMs separately. In the end of each kernel, the samples of each SM will be aggregated together and form a table like this. This table consists of 3 columns. In the first column, we know the PCs of each sample. The second column tells us the store reason of instruction samples, and the last column shows us the number of samples collected at each PC. For instance, in the first row, we know that there's 16 instruction samples at PC 0x80, and they are waiting for memory dependency stores. However, from this table, we still don't know what instructions cause memory dependencies. We only know these instructions are waiting for memory dependency stores. To find the root cause of stores, we need to analyze instruction dependency. Here's an example of control flow graph annotated with GPU assembly instructions. Use registers are colored by red, and definition registers are colored by magenta. Using backward slicing, we can get its instruction dependencies. Note that there's a difference between the CPU backward slicing and the GPU backward slicing we use in this work. On GPUs, we have predicate instructions where this P0 indicates this instruction is only executed when P0 equals to true. So in the backward searching phase of backward slicing, we don't stop in this LDG instruction in block B1. Instead, we need to continue backward search to basic block B0 and find this LDL instruction to cover all the cases. So after constructing this memory instruction dependency graph, we still have some false positives. For instance, assuming that arithmetic instructions do not cause memory dependency stores, we can eliminate this edge from the instruction dependency graph. Then after pruning these false positive edges, we could still have some nodes have multiple incoming edges. In this case, we apply several rules to apportion the stores to its sources. The first rule is that with more issued samples, we blame more stores on the register definition. The second rule is that for a longer path, we blame fewer stores on the register definition. So in this case, suppose we have the LDG instruction that has 1 instruction sample and its path is 5 instruction. We also have the LDL instruction have 2 instruction sample and its path is 10 instruction. Then essentially we can apportion the same number of instruction samples on each path. Next, after getting store analysis result and the program structure, we're going to feed this information into performance optimizers and analyze the matched stores for each optimizer. Then the matched stores will be taken into performance estimators to analyze the potential speed up of each optimizer. Finally, only top performance optimization suggestions will be output to the optimization report. In GPA, we have developed a bunch of performance optimizers. On the high level, we can divide the performance optimizers into code optimization and parallelism optimization. Parallelism optimizations adjust the thread distribution on the GPU to increase the performance. Code optimization modifies the suggest optimizations to modify the code to improve performance. We can further classify code optimization into decrease instruction costs and high latency. Decrease instruction cost optimizations, such as strength reduction, suggests to replace costly instructions with cheap instruction or eliminate them completely to improve performance. Latency hiding optimizations, such as loop unrolling, suggest that we can rearrange the code to hide these stalls to improve performance. Here are two specific examples. For strength reduction optimization, we match long latency arithmetic instructions that cause execution latency. For instance, we have long latency type conversion instructions and division instructions. It suggests we can improve the code by replacing long latency instructions with some cheaper instructions that are mathematically equivalent. Loop unrolling optimization is a latency hiding optimization. It matches samples such as significant memory execution or synchronization dependency stores exist in a loop, and both the store source and the destination instructions are within the loop. It suggests that we can unroll the loop aggressively if the compiler failed to do so. Next, based on the type of optimizations, we derive different estimators to estimate their potential speed up. For code optimizations, we have decreased instruction costs estimator and high latency estimator. Suppose that we have total number of T samples in this kernel, and the matched samples for an optimizer is M. The speed up for decreased instruction costs optimization could be estimated as T over T minus prime. An example is strength reduction optimization. For the code on the bottom left side, the strength reduction optimization suggests that we can eliminate this costly I2F instruction and instead store floating point values on the GPU directly. Then essentially the speed up we gain is by eliminating this instruction. Then for the latency hiding optimizations, beyond considering total number of samples, active samples, we also need to consider the matched store samples denoted as M subscript S. Then the speed up is bounded by both the active samples and matched store samples. An example is code reordering optimization. For the same assembly code shown on the bottom right side, the reorder code optimization suggests that we can rearrange these IAD instruction to fill in the store cycles to improve the performance. In practice, we observe that optimizations such as loop unrolling only rearrange code in a specific scope. So essentially, only instructions within the scope can be used to hide latency. In this case, we denote the active samples of scope as the sum of active samples of all its nested scopes, and the matched samples of scope is the mentioned sample within the scope itself. For the program structure on the right side, we can estimate the speed up of loop 2 as the total number of samples over the total number of samples minus the minimum of the active samples of loop 2 and loop 1 and the stored samples in loop 2. We also developed estimators for parallelism optimizations, which considers the thread distribution on SMs. Suppose we have a kernel which occupies only one SM and each block has 256 threads. Then essentially within this SM, we have 8 warps spread on 4 warp schedulers. If we're gonna change the thread distribution to 2 blocks and 128 threads per block, then each SM only has 4 warps. In this case, to estimate the speed up, of parallelism optimizations, we estimate the workload distribution change multiplies the latency hiding change inside each SM. Here's a detailed example. After applying GPA for the X-tensor case study, we analyzed X-tensor's tensor transpose kernel. In its performance report, GPA sorts each optimization based on its estimate speedup. Then under the optimization headline, we have several hints that suggest how to change code to improve performance. Below it, we also provide several hotspots to show in which code we can apply the above optimization. Specifically for this code, GPA provides two most significant optimizations, including strength reduction and global transaction reduction. GPA suggests that on line 3, we can replace this integer division with a multiplication by its reciprocal. The estimate speedup is 1.06x, and we finally achieved 1.11x. Next, on the same line, GPA suggests replace global memory reads by constant memory reads if elements are shared between threads. The estimate speedup is about 1.05x, and we achieved 1.03x by applying this optimization. We also applied GPA to a broad range of benchmarks, including Rodinia benchmark, Quicksilver, Minimalt, and Pali-C. We evaluated these applications on an Intel CPU with NVIDIA V100 GPU using CUDA 11.0. On the right side, we can see from this histogram that our estimated speedup and the achieved speedup by using the optimization suggested by GPA is quite close for most of the benchmarks. Those two benchmarks are two outliers. For the BFS benchmark, we apply loop unrolling to aggressively unroll the loop. However, in this application, we observe that the workload across different threads are quite unbalanced, so that loop unrolling only benefits a few threads. In this Pathfinder benchmark, GPA suggests to reorder the code to improve performance. However, since there's a synchronization within the loop, the code range that we can apply reordering is quite limited, so that we only end up achieving less than 1.10x speedup. In a word, GPA is a tool that provides insightful performance report to guide performance optimization for GPU kernels on NVIDIA GPUs. We also developed new capabilities since the paper. Now that GPA can use both instrumentation and instruction sampling to collect performance metrics, GPA can use instrumentation-based metrics to improve store attributions accuracy and construct new advisors. We also developed analysis capability to analyze new instructions on Turing and Empire GPUs. Now we can analyze instructions including uniform data path instructions, indirect memory access instructions, and asynchronous memory copy instructions. For any questions about the tool, you can contact us through the emails below. This tool is available on GitHub. This presentation and recording belong to the authors. No distribution is allowed without the author's permission. Thanks for watching my talk.